Welcome to MathMuni. Can you solve an integral without integrating? Usually not, but sometimes it is possible. And this integral here is a classic example of such a situation. So this integral looks fairly complex. In fact, it frequently shows up in texts on complex functions where a technique called contour integration is used to solve it. But there is a simpler way, as we shall see soon. Our first instinct is to think of some smart substitution that unravels the integral. We would be especially keen to get rid of that square root because that is usually a sign of complications. Those are all reasonable initial ideas, but before we go there, let's take a minute to understand the integrand here. Let's denote the integrand by y. Therefore, y is equal to the square root of x minus a times b minus x. Taking the square of both sides, we get y square is equal to x minus a times b minus x. Opening up the right hand side, we get y square is equal to bx minus x square minus ab plus ax. The right hand side can be written as b plus a in brackets times x minus x square minus ab. Moving all variable terms to the left hand side, we get x square plus y square minus b plus a times x is equal to minus ab. Now on the left hand side, we will be looking for an opportunity to create a perfect square from the x terms. So we add b plus a upon 2 whole square to both the left hand side and the right hand side. This can be written as x square minus 2 times b plus a upon 2 times x plus b plus a upon 2 whole square plus y square. And on the right hand side, we get b plus a whole square minus 4ab divided by 4, which can be written as b square plus a square minus 2ab upon 4, which is equal to b minus a upon 2 whole square. Therefore, this equation can be written as x minus b plus a upon 2 whole square plus y square is equal to b minus a upon 2 whole square. Notice that this is the standard form of the equation of a circle. The center of the circle has the coordinates b plus a upon 2, 0. And the radius of the circle is the square root of the right hand side, which is equal to b minus a upon 2. What else do we know about this circle? If you go back to its original equation, y square is equal to x minus a times b minus x, we notice that y is equal to 0 when x is equal to a and when x is equal to b. Therefore, the circle cuts the x-axis at the points a0 and b0. We are now in a position to plot this circle on the Cartesian plane. We have the x-axis and the y-axis. We have determined that the circle cuts the x-axis at the point a0 and at the point b0. The center of the circle is the midpoint of these 2 points with coordinates b plus a upon 2, 0. We're now in a position to draw the circle. And now if we were asked to find the area of the top half of the circle, the semicircle that lies in the first quadrant, as represented by the shaded area. The area of this semicircle could be expressed as an integral of y dx, where x goes from a to b. And this is equal to integral a to b, the square root of x minus a times b minus x dx. But notice that this is exactly equal to I, the integral that we were given at the start. Therefore, I is nothing but the area of the semicircle. And this area is equal to half of pi times the radius square. The radius is equal to b minus a upon 2 as determined earlier. Therefore, I is equal to pi upon 2 times b minus a upon 2 whole square, which is equal to pi times b minus a whole square divided by 8. So just like that, we have our answer. No integration, definitely no contour integration. Moral of the story? Before jumping into the mechanics, give yourself a minute to observe and understand the problem or integral or equation or whatever is in front of us. Sometimes there is a smart move that comes out of that observation that saves us a lot of tedious work afterwards. I hope you had fun, and I will see you back at MathMuni for the next story where mathematics comes to our rescue and saves the day. Meanwhile, check out mathmuni.com for hundreds of mathematical problems across a range of topics. We are rapidly expanding our collection and would love to hear your feedback. Please drop your suggestions in the comments below. Bye for now.